how I'm attempting to build a 2000 watt SFXL power supply. I recently stumbled upon Inner Science's server PSU reference design, and it blew my mind. Imagine this, a 2000 watt output at 12 volts with a full load efficiency of 95%. When I saw the specs, my first thought was, no way, that's insane. The footprint is only 185 by 65 by 36 millimeters. Seeing that much power packed into such a tiny enclosure immediately got me thinking, how cool would it be to cram this tech into an SFXL form factor? I mean, the beefiest SFX unit on the market right now, from Cooler Master, only hits 1300 watts. These server units are significantly smaller than an SFX PSU, yet push way more power. So the big question is, how do they pull it off? Full disclosure, I was an electrical engineering major in college, but back then I didn't know the first thing about actual PSU design. My focus was the grid, the massive infrastructure connecting power plants to factories. To figure this out, I went down a rabbit hole of Tier 1 manufacturer reference, designs, and teardown videos. After a deep dive, I finally cracked the secret sauce. The short answer, they use a dozen different tricks to shrink the footprint, but the real MVP is the switching transistor. Every high-density server PSUI looked at had one thing in common. They've ditched traditional silicon for wide bandgap semiconductors, like gallium nitride, GaN, and silicon carbide, SiC. But does just swapping the switches automatically shrink the unit? Not exactly. To understand why these materials change the game, we have to look at the architecture of a modern PSU. A typical high-end unit consists of an EMI filter, active PFC, an LLC resonance circuit, a high-frequency transformer, and synchronous rectification. The magic happens in the PFC and LLC stages. By using GaN and SiC, we can crank the switching frequency way up. According to the formula for magnetic components, as frequency increases, the required inductance for the PFC choke and the high-frequency transformer decreases. Smaller inductance means smaller physical components. Since GaN and SiC have much lower junction capacitance than traditional silicon MOSFETs, their switching losses are negligible by comparison. This allows them to run at frequencies that would melt a standard MOSFET, which is exactly how these server units get so tiny. Beyond the semiconductors, these manufacturers have a few secret weapons that I've borrowed for my own design. Bear with me, this gets a bit technical, but it's crucial if you want to understand high-density power design. In these ultra-compact units, manufacturers save vertical space by mounting the switches and drivers on daughter boards. While a standard PSU usually has transistors standing upright on the main PCB like little tombstones, these pros lay them flat. They use bottom-side cooling. Basically, the PCB is peppered with thermal vias that magically wick the heat away to a heatsink on the back of the board. It's incredibly slick. Furthermore, some designs utilize interleaved PFC. You might think, wait, wouldn't using 2 inductors and 2 switches instead of 1 take up more space? I thought so too, until I saw the math. When switches cycle, they create ripple current. If you run 2 phases 180 degrees out of sync, the ripples cancel each other out. The effective ripple frequency doubles, and the peak amplitude drops significantly. This is a massive win for the EMI filter. Additionally, to avoid magnetic saturation at high currents, a single inductor needs a huge core. By splitting the load between 2 smaller coils, the total volume doesn't actually increase, but the total heat loss is cut in half, saving precious thermal headroom. I even saw one vendor use a coupled inductor wound on a single core with 2 posts. Absolute genius. To chase that last 1% of efficiency, some designs have deleted the bridge rectifier entirely. In a standard boost circuit, you're converting AC to DC, but the diode drops in a traditional bridge are a huge waste of energy. Instead, they use a totem pole PFC circuit. It uses the active GaN switches to handle both rectification and power factor correction simultaneously. Of course, there's no free lunch. When you flip switches that fast, you get massive ringing and oscillation. To mitigate this, the gate driver circuit must be hugged tight against the switch. For GaN, you almost always see Kelvin connections, a dedicated return trace to the driver's ground to prevent interference from the massive switching currents. Then there's the skin effect. At frequencies in the 500 kHz to MHz range, current hates travelling through the centre of a wire. It only wants to flow on the surface. Traditional thick wire becomes useless. These designs use Litz wire or even integrated PCB windings. It sounds crazy, but since PCB copper foil, 1 to 2 ounces, is so thin, the current actually utilises the entire cross-section of the trace more efficiently than a thick wire would. In 48 volt designs, they even stack the primary and secondary windings to minimise flux in the core and further reduce volume. At these frequencies, standard aluminum electrolytic capacitors develop high ESR, making them run hot and fail early. Ceramic capacitors, or MLCCs, however, thrive here. I'm placing high voltage ceramics right at the feet of the switches, so the current hits them the millisecond it exits the transistor. When you push power density to this limit, everything gets a little mad scientist. Every millimetre of space and every milliwatt of heat is a battlefield. I've only scratched the surface of the clever engineering involved here. In next part, I'm going to break down exactly how I tackled these challenges. I'll show you how I went from knowing absolutely nothing to designing my own custom PFC and LLC stage PCBs in just 2 months, turning all this theory into actual physical hardware based on my own understanding of the craft. See you next video. Bye.